So last time I basically spent the whole time just to review about MaxFlow, and today we just gonna now really solve approximate sparsest cut fast. Okay, so let me review the question. The question is just this: the sparsest cut problem, right? You have a graph, and you have, let's say, some parameter phi, and you ask if G is a cut expander, or in other words, is there a phi sparse cut in the graph, right? This is just if and only if no phi sparse cut with respect to 2 degree of G, right? So you can ask this. It's just a natural question if the graph is an expander or not. And one sec, did I turn on? Okay, I think so. All right. And if you can solve this one, then you can binary search for phi, right? And then you would see if there is a phi sparse cut or not. Okay, so that's like if you want to find a sparsest cut, it's enough to solve this one just by binary search. However, this is hard. This is NP hard, and there is just no polynomial time algorithm, assuming that P is not NP. And you can have a look at the citation here, but yeah. So this is bad news because like checking if there is a sparse cut is the key subroutine in basically the whole theory that we have developed. To find expanded decomposition or to find this expanding balance separator, you just kind of keep finding sparse cut and repeat something, right? So if you cannot find sparse cut, that's bad, okay? And now, but we actually saw that you can solve the approximate version of this problem in polynomial time. Can anyone recall how? As in, like, I either say that the graph is phi expander, that is, there's no phi sparse cut, or I find phi log n sparse cut. I can do that. Actually, in polynomial time. How did we do it? Anyone? Is there when we try to prove flow cut gap? How did we do this? Anyone recall? Okay, I will then remind you. Okay, so actually we can do this for any node weighting D, and what we can do is this. First, we can just check first, right? If let's say you have the node weighting D, then look at the product demand for D, and then just check if this is routable. If the product demand is routable with low congestion, let's say 1/phi. Checking if this is routable is in polynomial time. Why is that? Because checking this, you can model it as what? As a linear program. And linear program can be done in polynomial time, can be solved in polynomial time. So you can really just check this. And if it's true, then it means that like if the product demand is routable with congestion 1/phi, then any d respecting demand can be routed with congestion 2/phi. So it means that d would be flow expanding to phi/2 flow expanding, which means that it's phi/2 cut expanding. Okay, so that's the first case. So if it's routable, then you can say that it's cut expanding. But if not, if actually the congestion is larger than 1/phi, then you remember like we look into the dual of the LP, and then we find a sparse cut from that. The sparse cut that we find is like phi log n sparse cut. Okay. So it means that in this case, it just means that D is not phi log n cut expanding. So we either conclude that it's phi expanding or not phi log n expanding. So this is like log n approximation. Right? So this is, we actually know some algorithm, some approximation algorithm. Okay. But it's not so fast. Like this requires solving LP, right? And solving LP in general might not be so fast. So now, today we're gonna see log square approximation. And the running time is gonna be something like this, where T of M is just a time to compute max flow in a graph of size M. When the graph have M edges, that's T of M. So you take like log square max flow calls plus some nonlinear term. Okay. And right now we actually know that T of M is nonlinear. It's almost linear. Okay. So by the way, sometimes I will call this thing Polylog M near linear. And this thing almost linear. So this is considered better because like polylog, like this little one in the exponent can be worse than polylog. Okay? And it's a technical term that people agree to call it. Like when you just have polylog overhead, then it's near linear. If it's enter little one overhead, then it's almost linear. I don't know why, but it's just how it is. Yeah. So this is almost linear, not quite near linear, but good. Yeah. Okay. So it means that this thing in total is just almost linear time. So which is really fast, which is great. Okay. So that's the goal today. We're gonna get the way to find approximate sparse cut in almost linear time. Okay. All right. So in particular, we're gonna solve a more general problem for any node weighting D. And so given the graph G, any node weighting D and phi, we either find a phi sparse cut with respect to D, that is D is not phi expanding, or with high probability we conclude correctly that D is phi over log square expanding. So there is a gap of log square, but yeah, and that's the running time. This is the running time. Okay. So that's the goal today. Okay. And let me recap quickly again what we showed like last week, right? The first thing is that it's about flow decomposition, right? So if you have a single commodity flow, right? And let's say F route from source to sink, exactly route this source function to this sink function, okay, with congestion kappa. Then like this, like if there is a flow F that route this source function here to the sink function here. Okay. Then we have seen that by decomposing the flow into paths and so on, it means that there exists another bipartite graph M, right? Where the node weighting of M here just agree with the source and the sink, okay? And this M is routable in G with congestion kappa. And the number of edges of M is just number of edges in G. Okay. And we can compute this M given, given F in nonlinear time. So, right, given this flow, you can basically extract how the flow start, for each flow path, how it start and end, which is this meshing in nonlinear time. Okay. So that's what we showed last time. Okay. And the second one is this picture. Okay. So let's say you have a graph, a source function, and a sink function. And just imagine that you try to send flow, like maximum flow from source to sink, right? So then we just observe what happened. And basically, just by using one MacFlow call, we're gonna get some set L. Okay? Think of L as the min cut that separate the source from sink, right? And what we're gonna get is two things: the flow on the left and the flow on the right. The flow on the left of min cut and the flow on the right of min cut. And how does it look like on the flow here? The flow on the left is just stay on G of L, G induced by L, just stay inside here, right? And it will respect the source function, which is it will respect this source function, which is source intersect L. So it only sends flow from this source. Some of it doesn't get to be saturated, but yeah. So it respects this source function, and it will saturate the sink function on the left, which is what? The sink function on the left is just the node weighting of the cut, which is this thing, and the sink inside L. Okay, so everything, this is like the sink on the left, and they will be saturated from the source. Yeah. Is the picture clear? Okay. Right. And similarly, the same thing happened on the right. Right. So everything, like all the source, on the right, what happened is that you think of this as a source on the right, right? The source on the right will be sent, like the flow on the right will saturate this source on the right. So everyone here will send something, and it will end at source on the sink on the right, which is this guy, intersect. So this guy are saturated, and the flow just respect this guy. So some of it is not saturated. Okay. So this is just the structure of MacFlow. Like when you have source and sink, you compute MacFlow. You can basically you get this MacFlow is just concatenation of flow on the left and flow on the right. Okay. So now this is like just the two things about MacFlow that we're going to use. Okay. Now come back to our main algorithm. Okay. So below, now I'm just going to present you the approximate sparse cut algorithm. And for your convenience, just think of the node weighting as all one vector from the beginning. But basically everything just generalized. But I'm just going to present it with general node weighting, but you think of this thing. Okay. So the algorithm is this. First, we just initialize. You have a graph as an input, but then you initialize different graph x. Okay, this graph is going to be empty graph, but it shares the same vertex set. Okay. So you have graph G. You initialize another graph x, right? And then now think of this graph x as the graph where you play a cut matching game, right? In cut matching game, you start with empty graph. Okay. But this is different from G. And then there are log square rounds, which is the round of cut matching game. In each round, what do? So first, the cut player will just read this X graph, the cut matching game graph. And then it's just going to choose the set to set A and B, the cut. Right? That's what the cut player do. Just look at the graph X and choose A and B. Now, given this A and B, okay. So, okay. You have graph G and you have graph X. Then the cut player choose A and B. Okay. Now you look at this A and B in G. Look at the same A and B in G. And then you compute some flow on this graph G. So what is this? Okay. By the way, this flow cut here, I really just mean this subroutine here. Okay. Where it's just kind of about computing max flow in G, where the source is source and the sink is sink here. Okay. So what do? We compute max flow where the source is kind of from A, intersect your node weighting, send from your node weighting on the A side to the sink, which is the node weighting from the B side. In which graph? In the graph G, when you scale up the capacity by 1/5. This makes sense because you are thinking of phi flow expansion, which is about checking if your demand, the respective demand can be routed with congestion 1/5. So you just scale this thing up to 1/5 so that if you can route in this graph, it means that the congestion is at most 1/5. Make sense? Okay. So you just compute max flow in this graph. Okay. And you're going to get flow on the left, flow on the right, and some min cut L. Okay. Now, the claim is that if L is not empty, suppose that your min cut is not empty, then you can just return L. Okay. This L is going to be sparse cut. We're going to prove this. Okay. On the other hand, if suppose that L is empty.
Is Li a set of vertices?
Yeah, Li is a set of vertices. Yeah. So Li is this is Li. This thing is L. Okay. And for this picture, suppose that L is empty. If this is source, if this is source, this is sink, L could be empty, like L could be empty. In this case, it means that there only exists, you only have flow on the, well, you only have flow on the right, which means that it will just basically just saturate. If L is empty, what is this? Then this thing would be just the whole, just be the whole source, and this is just the whole sink, right? And it just means that everything, all the sources are saturated, and this flow will respect the sink. So when L is empty, this is just the flow. F on the right is just the flow that saturates source and respect the sink. Respect original source and respect the original sink. Okay? So that's what happens when L is empty. So it means that here when Li is empty, then we basically saturate this source and respect this sink. Like we get this, like we get a flow. This flow would saturate. The flow on the right would saturate delta I and saturate delta I and respect sink I, nabla I. So then we just look at this, like look at this flow on the right here. That's just saturate the source. So now I let Mi be the bipartite graph routed by Fi, Fi on the right. So in particular, if you think of this D to be all one, Mi is just going to be really just bipartite matching from Ai to Bi, where everyone in Ai is matched, right? Because it's saturated source. Good so far? Okay. And what we do next, we just add this matching to graph X. And that's the end of the round. Then we go to the next round. If we keep repeating this round for log square rounds and nothing happened, we didn't find any sparse cut, then I'm gonna claim that by now, it must be the case that D is expanding in G. Okay, let me show you like a picture of how things goes again. Like, so think of this as the graph G is like the matching player world, okay? And the graph X is cut player world. Cut player doesn't directly see G at all. Okay? It only works with X. Okay? So in each round, what happens is that the cut player look at the current graph X and choose Ai and Bi. Okay? And then this Ai and Bi, just define the flow instance in G. Okay? So we're just gonna send max flow in this graph as a scale up capacity from the node waiting on the AI side to node waiting on the BI side. We try to send flow from here to here. Okay. So, and then if the flow is like, let's suppose that the min cut is empty, Li is empty. Then what we're gonna get is just some flow that's saturated node waiting on AI side to some, and it's sent to somewhere in BI. This flow corresponds to some matching, which we can extract. Just how the flow path look like, just extract that, and that's the Mi. And the new graph Xi is just union this Mi. If This is the case when Li is empty. If Li is not empty, it just return that as the cut. And I'm going to claim that that's a sparse cut.
Yes.
So just repeat this log square round. Is the algorithm clear? Okay. Yeah.
I thought the cut player chooses like the matching. Is it chosen by the matching player?
The cut player just choose AI and BI.
Oh.
And then you see from the cut matching game, from the cut player's perspective, it chooses AI and BI. It doesn't know how does the matching look like, but the matching will just come from the matching is kind of arbitrarily defined from this flow. It's just some matching that match AI to BI. This matching can look arbitrary, but it's just matched from AI to BI. Okay, so this is like this MI, like this flow is like the matching player. The matching player define computer flow that define this matching and feed it to cut player. More question? Yeah.
Just to see if I remember correctly from what we learned from the cut matching game, is like we already saw a locked word and strategy for the cut player to handle against any matching player.
Yeah.
And it's fast too.
Yeah. Yeah.
Okay.
So as long as the cut player choose AI and BI and the matching player match everything in AI, then we guarantee that after a few rounds, the union of this matching must be expanding, must be an expander. Okay. And in each round, this can be found, like AI and BI can be found fast. Yeah.
How do you guarantee that everything in AI is matched?
Because when Li is empty, then we know that all the source must be saturated by the flow.
Oh.
Right? Like if in the case when Li is empty, we know that the flow on the right saturate this thing, which is when Li is empty, this is just, this whole thing is just the original source. And this whole thing is original sink. So we know that this thing saturate original source, which is just AI in our case.
If Li is like the entire V, it's just the other way around.
Yeah, if Li is an entire V, then it's just gonna be opposite direction. That is, like we get some flow that respect this side and saturate this side. Okay, more question about this algorithm description before we analyze it. Okay, good. So, yeah, I want to note again that the cut player only sees the graph X. It never directly accesses G, but it still relates to G somehow because each matching M is kind of, it's a flow, it corresponds to flow in G, right? But it just accesses the graph via the matching. Okay, so it doesn't work like from cut player perspective. It's just we just on the graph X. Okay. And yeah, each matching MI is a valid matching that is required by the cut matching game. Because what we need from the cut matching game is that when you have AI and BI, everything in AI is matched. And it's the case here. Okay. so just because, yeah, this flow on the right saturate all the source. Okay. So so MI is gonna, like for general node weighting D, MI will look like a bipartite graph between AI and BI, such that, the degree of everyone in A is just D, which is the source, the source at A. Okay. So what we get so far is that I hope you're convinced that like the meshing that we feed to the cut player is a valid meshing for the cut meshing game. And we know already that if that's the case, then after R square round, then D is going to be expanding in graph X, not G, right? This is what we just conclude so far. It's expanding in X. Right? This is just the lemma only about cut player. We conclude that this node weighting is just going to be expanding in the graph, which is the union of this bipartite graph. Okay. So what we want at the end of the day is that this thing should be expanding in G, but we kind of get something close. Okay. So now let's really analyze this algorithm. There are two cases. Either we find a sparse cut or we conclude that D is expanding. Okay. So, okay, let's talk about running time first. So there's nothing much really. In each round, if we exclude the time for the cut player, we just solve this thing, which is just to one call to max flow. And then we do flow decomposition to extract the meshing from the flow. That's M log n. Right? This is just to get MI from the flow on the right. This is just flow decomposition. Okay. And I remember I didn't talk about how to do this last class. I just said that using link cut tree you can do it, but can have a look if you want to know how. But for the total time for the cut player, okay, like if the node weighting is all one vector, do you remember the running time that we conclude in class? What's the running time?
For the cut matching game?
For the cut player.
So if we just have the normal one node weighting, would it be all of m log to the fourth n? Or
N, yeah.
all of m
M?
times log to the fourth of n?
Yeah. Actually, a bit better, because this is just all one vector.
Oh, yeah, so it's just n.
Exactly. Like, we kind of just have this time, right? Like, in each round, 2 log square. In each round, you spend ni time, right? So that's n log to the fourth. Yeah. But in general, when this is not all one vector, you're gonna get that if each meshing here has at most m edges, then in each round the running time is like mi. So this is then like m log to the fourth. Okay. So this is kind of like what I claim and I didn't prove, but yeah, it's kind of believable. Yeah, but yeah, because yeah, I didn't prove this, but the idea is just like here in each round, you kind of average flow along matching edges. There are n matching edges, and we need to average flow like I round for the I round robin walk, right? Here, like you average flow along m many edges, and there are m many matching, I many matching in I round. So that's why the running time is mi. Yeah, but yeah. Okay. So that's the time for the cut player. This is the time for the matching player. So in total, this is the running time. There are log square rounds, and this times log square is absorbed by this thing. So this is running time. That's easy. It's fast for sure. Now let's see the correctness. Okay. The case for sparse cut. So my claim is that if Li is not empty, then you get this, that number of edges crossing Li, the cut size of Li, is small compared to node weighting from both sides. Just means that like Li is a phi sparse cut with respect to D. Okay. So this is actually quite simple. Okay. And okay, maybe it would be nice if I draw actually. Okay. Good. Okay. So suppose that I have this graph. Okay. And this is AI. This is BI. Okay. So this is like the source. The source is like node weighting from the A side, and this is a sink, right? Okay. There's only one pen in this room. Really? Wow. Okay. Okay, many. Good. All right. Okay. So we try to send flow from here to here, right? And then what does it mean? Like if we can saturate the source to sink, then it's kind of there's no bottleneck. You send all the source to sink. But otherwise there is bottleneck. That's why like the reason that Li is not empty is kind of basically there's a bottleneck that prevents you from sending source to sink. Okay. So maybe the cut looks like this. This is Li. Okay. And then let's say that and we solve this in a graph where like know that we solve this thing in this graph, right? in this graph. Okay. So what do we have so far? We know that there is a flow on the left, which basically maybe like it saturates the sink on the left. Like everything here is saturated. Okay. So let's look at flow on the left. Okay. So the flow on the left here, first is it respect this part. Okay. So like this thing intersect L, yeah, which is just and saturate saturate node weighting on the cut of L and this thing. So saturate it saturate the cut plus the sink, maybe the sink. This is like BI. So it saturates BI, like this thing, the sink on the left. Okay. So if it respects this thing and saturates this thing, it just means that the size of this is smaller than the size of this. Right?
Yes.
Okay. So, like, yeah. This thing, this whole thing is smaller than this thing. Oh. Yeah. So in particular, I know that like this is, by the way, this is the node weighting in G prime, right? This is in G prime. Okay, so like this capacity of this guy is smaller than the capacity of this guy. That's the. So what do we have here? It's just, in particular, the size of this thing, which is, let's say the cuts in G prime of L, okay, need to be smaller than the size of this, which is just D A I intersect L I. Right? This whole thing is smaller than this, so this size only is smaller than this one. Okay. But what is this thing? This is like 1/5 times the number of edges in G from Li to. I have 1/5 here because this is like the total cut size in G prime. But this is just this number in G. But this one, well, it's just at most D of L. Okay, so we prove one side that this one is less than this. Okay. So like, but intuitively, it's really just kind of say that, the cut here need to be smaller than this thing. So like, it just said that the cut after even scale up by 1/5 is smaller than the source. Because like otherwise you wouldn't get stuck. Otherwise the flow would have been sent successfully. So this cut after scaling up by 1/5 is smaller than the source. That's how you get one side. Okay. What about another side? Well, like you now just look at, like, let's prove this one too, that this thing is less than this side. It's just kind of symmetric. We just look at the flow on the right, right? And you know that everything here need to saturate. Like the source here needs to saturate this thing. Okay, on the right here, the source on the right saturate the source. The source on the right is saturated and respect the sink on the right. Okay, so we have that FR saturate this node weighting in G prime again, okay, plus the source on the source that is outside L, so which is what outside L, okay. And it respect this thing, which is D intersect BI and outside L. Okay. So from here, it means that this thing needs to be smaller than this. Okay. So I just said that look at this only. This thing need to be smaller than this one. So the size of this is smaller than D of this thing. Which is smaller than D of V minus L. But this is again like a 1/5 times, the cut size in G of L. Are we good? So we conclude this. This is just some calculation, but the intuition is really clear, by the way, right? You got stuck, like you have some L because you got stuck. You got stuck because like the source here is just too big for the cut. So the cut here needs to be smaller than this side. And the cut here needs to be smaller than the sink on this side. That's it. Okay. So I just prove it. Now let's look at the expanding case. So you agree that if we get some non-empty Li, we are done. Get sparse cut. And next we will try to prove that if the game proceeds for a log square round, then we can now conclude that D is actually something like phi over log square expanding in G. So we have concluded before that, okay, just by the cut matching game, D is something like constant expanding, or even 1/2, I guess, expanding in X. Do you have some guess how come we, like if it's expanding in X, why it should be expanding in G as well? Why is that? Any intuition about this? Yeah.
X is just a bunch of flows in G, and so if we can route flow within these flows in G, and we should be able to just route it in G directly.
Exactly. Like X is really just a union of matching. Each of these matching, you route it in G. So the whole X, which is union of R many matching, can be routed in G with condition R. Right? So this is a whole graph that can be routed in G with low congestion. And if there is some demand that you can route in X with low congestion, it can be routed in G with low congestion too, just by concatenating, like composing this flow together. That's why, that's the intuition. So let's prove this formally. Okay. So from the cut matching game, D is flow expanding in XR. Okay. Just mean that look at any D respective demand, like any D respective demand, capital D, this is routable in X with congestion at most 2. You can write it in this way, right? This demand is routable in X with congestion 2. Just we have this notation. D is less than 2X. D can be routed in X after you scale X up by congestion by factor 2. Now, I want to claim that X is less than G, okay, by some factor. Why? Because X is a union of Mi, and now this Mi is routable in G. Like, okay, sorry. I claim that this thing is routable in G with condition R over phi. Why is that? Well, each Mi can be routed in G after you scale up the capacity by 1 over phi. Like this thing literally just route Mi in this graph with condition 1. So it means that Mi routable in G with congestion 1 over phi. So the union of R mini matching would be routable in G with condition R over phi, this is just XR. So that's why we can conclude this thing. XR is routable in G with condition R over phi. Now, just composing these two things. Right? Then we would get that D is now routable in G with congestion 2R over phi. So any D respective demand can be routed with congestion this much. So it means that the node rating D is flow expanding with this parameter. Okay. Any question?
What was the probability? Did we just say it was high probability?
Yeah, so like this is kind of, when we say high probability, I usually say means 1 over 1 minus 1 over poly n, and this poly n thing of n to the 100, yeah, like something big.
Right, got it.
And this is something that we kind of conclude from the cut matching game, right? That we can make this to be like basically any poly, like this poly n can be any poly n, polynomial n. Like this is like arbitrarily small. Yeah. Okay. Questions? Yeah.
I had a question from 2.4 actually. It sort of has to do with the drawing you did on the whiteboard.
2.4.
Or it's
Yeah.
just about this cut, like on the whiteboard, the
Yeah.
AI cut. It's like, it's not an AI BI, like how do we call this type of cut? Because I feel like it's kind of, I was thinking it's not like an AI BI cut, but it's more like we're cutting some demand or something. I don't know, like what, is there a name? It just seems like a different.
What's the name for AI and BI, you mean? Or
No, it's just like the cut ally that we're considering. Like, what is it cutting actually?
Oh,
It just feels like a new perspective of a cut that I'm not that familiar with. Like,
so what is LI? LI is literally just like when you have the source and the sink here, and if you consider when you add a super source where this guy get capacity source of V and do this, and then you have super sink and you connect this with capacity sink of this node V, and when you compute min cut in this graph, the min cut can look like this. In this case, Li is empty. The min cut can look like this. In this case, Li is the whole graph. Otherwise, min cut can look like this,
okay.
which is just here.
Okay. Thank you. That's very helpful.
Yeah. And in MacFlow, normal MacFlow, when you get min cut, you just know that like the source can send flow, can saturate. The source can saturate all edges in the min cut, and the min cut can, like there is a flow that saturates the min cut edges to the sink. So that's just correspond to this drawing.
Okay.
Okay. More questions? So yeah, today we just start to get fast algorithm for the most basic thing, and but you see, like getting sparse cut is not quite enough. Like what we want is expanded decomposition and expanding balance separator. And should I do it now or?